let's graph 6 basic functions. The first one we're going to graph is the constant function f of x equals 2. The graph of that, remember f of x can be written as y equals 2. And if you're not sure if that's a horizontal or vertical line, make a t-chart, and since y is 2 everywhere, there's a 2, 2, 2, and that means x can be anything. And if you graph these 3 points, you'll see it's horizontal. So 1, 2 is that point, 2, 2, and 3, 2. So the graph of f of x equals 2 is a horizontal line. Now the domain and range. The domain is how far left and right the graph goes. And so in this case it goes from negative infinity to infinity. And the range is how far up and down the graph goes. So in this case we see that the graph doesn't go up and down very far at all, it just stays right at 2. So instead of an interval, I write it as a single point, which is called a singleton. So that's the range. Now, let's move this back up and graph a linear function. So f of x is equal to, let's just do 2x plus 1. And that's a nice linear graph that looks like this. Now remember, this is y equals, let's see if I can, okay, let's see if we can do that again. So here we're going to do y equals mx plus b, where b is the y-intercept. So we'll go up 1 and put a dot. And 2 over 1 is the slope. So slope is rise 2, run 1. So that's from this point right here. So rising 2, run 1, and put our second dot. Rise 2, run 1. And we can connect that. No, not perfect, but it's okay. Okay, now let's do the domain and range. So how far left and right, that's how many of the x values show up on this graph. So this arrow right here and then that arrow up there shows that the graph goes all the way to the left and all the way to the right. So these are the x values, and that's the domain. Then how far up and down does the graph go? Well, we can see, let's move that over, that the graph goes all the way up and all the way down. So up here because the arrow goes up, and then down there because the arrow goes down. Those are the x values that this graph takes on. Excuse me, the y values. So negative infinity is all the way down, positive infinity is all the way up. Now, we'll do a quadratic function next. So let's do it as f of x. So we'll write f of x, since we're dealing with functions, is equal to, now in this one, let's just do the basic quadratic x squared plus 1. So what we have is this x squared tells you it's the shape of a parabola, and if we make a t-chart just to guess where some of the points would be, plug in 0, you get out 1. That's the point right here. Plug in 1, you'd get out 2. Negative 1 would also give you 2. So what we see is this is a parabola that's been shifted up 1. So when we do the domain and range, remember domain is the x values. How far left and right does it go? So picture the graph. How far left and right does it go? It goes all the way left and all the way right. So it's negative infinity to positive infinity. Now, how far does it go up and down? Well, what we see is the graph has a lower bound right here of positive 1, and then it goes up to infinity. So we'll write the range as bracket 1 comma infinity, because it goes from 1 up to infinity. Now we still need to do, oops, sorry about that, a little jumpy. What do we need to do? A square root and an absolute value. So let's do the square root function next. F of x is equal to the square root of x. Now, the graph of this is going to be limited. We can't put in negative values because we don't want to take a square root of a negative. So the smallest value we can put in right there is 0. Square root of 0 is 0. And then I can plug in 1. And then I'm going to jump up to 4 because that's the next perfect square. So 0, 0 is right here. 1, 1 is right here. And then 2, 3, 4. Let's say 4, 2 is right there. So this shape is kind of like that. It is a half of a parabola tilted on its side. So the x values are the domain, and the lower bound on that is 0. See that the graph doesn't go any further left than this. So 0 is my lower bound on the domain, and then I shoot off this direction towards infinity. Oops, let's change it to a pencil. So 0 to infinity. And then my range is how far up and down my graph goes. And again, what we see is this graph has a lower bound right here of 0 on the y-axis. So all these values up here are okay, but the graph stops. It doesn't go any further down than this. So this is a lower bound of 0 on the y's, upper bound of infinity. Now just to remind you, I'm going to tell you this is the x values that show up on the graph, and these are the y values that show up on the graph. So we still need to do a square root function. Square root function, f of x is equal to, no, we did the square root. We didn't do an absolute value. The square root of, excuse me, absolute value of x. So if we look at a t-chart, just give us some idea of some of the points. If you plug in 0, the absolute value was 0. Plug in 1, the absolute value was 1. And then if we plug in negative numbers, they also come out positive. And that's enough to be able to get the general idea of the shape. There's 0, 0. There's 1, 1. 2, 2 would be there. Negative 1, 1. Negative 2, 2. So it's similar to a parabola, except it's pointy. This graph has no curve right here. It's just a V shape. So again, we ask ourselves how far left and how far right it goes. So the domain, this graph goes all the way to the left because of this, and all the way to the right because of that arrow. So we see a negative infinity, comma infinity. And then the range, those are the y values. So again, your eyes are sort of drawn to the fact that it has a lower bound when you look up and down. So it goes from here up. The lower bound then will be included because there's the point 0, 0's on the graph. So 0 to infinity. And that's 5 functions, and we'll do the piecewise function in a separate video. We're going to graph the following absolute value function. And the reason we're doing this function is to practice with the transformations. So this graph has a basic shape, and that basic shape is sort of a V shape, and that's situated at 0, 0 if the function didn't have any transformations. So here's the graph of the absolute value of x. But we're going to do the following transformations on it. The negative sign right here makes the graph flip over so that instead of facing upward, it's going to face downward. The 2 right here makes the graph stretch. So what that's going to do is make the V a little bit skinnier. So I'll sort of exaggerate it right here. And I don't know, somehow skinny makes more sense than stretch, but that's not a real formal word. And then the +3 right here has the action of moving the graph left 3, and this transformation is an up 4. So let's scoot this down a little bit so we can keep it on the screen. Okay, here we go. Oops. Let's erase that and make it white. Okay. So the vertex on an untransformed graph was right here. But we have to move our graph left 3 and up 4. So when I do that, I go left 3, up 4, and that's the new vertex. We know the graph is going to be V-shaped and sort of skinny like that. So to figure out some points on this graph, let's make a t-chart. So let's rewrite our function down here. F of x equals -2 absolute value of x plus 3 plus 4. Now, to make a t-chart, we want to pick points that are around -3 because we know that's going to be the center of that V shape. So let's pick -2, and then we'll pick -4 because those are equidistant from the center. The center is right here. Then let's pick -1 and -5. So when we plug the value -2 in right here, we're going to get a value out of 2. When we plug -4 in, it's also going to give us a 2. I'm not showing the work for that, but you can go through and do the computation. When we plug in -1, we get out 0, as we do when we plug in -5. So I plot those points on my graph. I have -2, 2, -4, 2, -1, 0, and -5, 0. So I connect those points and I see that's the function. Domain, it goes all the way to the left and all the way to the right. And range, on the range you do the smallest value first. So the smallest value on the y's is right here. How far down does this graph go? It goes all the way down to -infinity. And then you consider how far up the graph goes. So you're looking here, how far up, and you see it has an upper bound of 4. So that's how the maximum y value. And the graph does touch a 4. It's at, we know, -3, 4. So that's the highest point. And that's the domain and range of this function. Let's graph the following piecewise function. You can think of piecewise functions as sort of a Frankenstein of other functions. So the first function is the function f of x is equal to 2x plus 1. But it has what's called a domain restriction. That's only when x is greater than or equal to 0. So the way to graph these functions is to think of them as separate functions and then just keep the part that it tells you to. So let's do this one, f of x equals 2x plus 1. Well, this is just a nice little linear function. So we graph that first, and here's what we get. Then this has an intercept of 1 and a slope of 2. So we can graph this line right here. Okay, but now we go back and we consider the domain restriction, and they told us that we're only going to keep the part where x is greater than or equal to 0. So we take an eraser and we just erase the part that we don't want to keep. Let's see, greater than or equal to 0. So we're going to erase all that. And we're just going to keep that. And this is a solid dot here because of the or equal to right there. This makes it a solid dot. Then we're going to do the second part of this Frankenstein function. And it was f of x is equal to -2. And we know that is only true, if we look back at the original problem, if x is less than -1. And we know that this function is a horizontal line at -2, so we draw a horizontal line at -2. But the domain restriction tells us that we can only keep the part where x is less than -1. So that would be from -1 to the left. So we take our eraser tool and we just erase the part that it tells us to not keep. Now this boundary, because of the inequality, is open. So right here, see, it doesn't have the or equal to. So strictly less than 1 has to be an open dot right there. And that's the graph of the piecewise function that is given by f of x equals 2x plus 1 if x is greater than 0, greater than or equal to, and f of x is equal to -2 if x is less than -1. Now let's do the domain and range. Being able to do the domain and range on these is tricky, but what it tells you is if you can do domain and range on these, then you really understand domain and range. So let's do the domain first. Remember, domain is how far left to right the graph goes, and that's because the domain is the set of all x values. Now, how far left does this graph go? Right here, this tells you the graph is going to go all the way to -infinity. So -infinity, comma, but then as your eyes look at the graph, you go over here and you get to -1, but that's an open dot. So we write -1, oops, but we have a union symbol on that. An open parenthesis first. So that's because of the open dot. Now we're going to jump, so we have to use a union symbol, over the values between -1 and 0 because the graph doesn't exist between there. Then the graph starts again at 0, and that's included. That's a solid dot there. So we're going to put bracket, 0. And then this arrow tells us the graph goes all the way over to the right, which will be infinity. And you're always use parentheses on and infinities. Okay, now let's do the range. Let's go over here. Remember, the range is how far up and down the graph goes. And that's because you're considering the y values. So let's look at the graph. Let's do how far down the graph goes first. So the graph is at a constant function here on the lower bound, right here. It's at a lower bound of, there we go. It's at a lower bound of 2, but that's a constant function. So the range starts at -2, and it's solid line on a horizontal, so we write that as a singleton. And then it jumps, and we're looking at the y values here. If you look, the graph doesn't exist between -2 right here and 1. There's no graph between these values, so we use a union symbol to denote a jump over those values. And then when we get to +1 and we go up to infinity, so we're going to use a bracket because it's a solid dot, and then we're going to go up to infinity. And so there we see the domain and range on our piecewise function. So just to go over it again, the way to handle these piecewise functions is to treat each function separate here, and then if you want to graph the whole thing and then erase like I did, just keep the part it tells you to, then do the second function, that was the horizontal line, and then I grabbed the eraser and I just kept the part it told me to. Then when I do domain and range, I look at the graph and I ask myself, for the domain, how far left and right, and for the range, how far up and down. The directions on this are to find the domain. So we have a rational function, f of x equals 2x over x plus 1. And what we're going to do is find or state the domain. The domain is the x values. And on a rational function, the concept that we're going to be using is that we can't divide by 0. Division by 0 is undefined. So I cannot have a 0 underneath this fraction. Anytime I had 0, it would make the whole thing undefined. So that's the only value for x that we can't have. So we take a look at this right here, and we say that value, that whole value, cannot be 0. So if I have x plus 1 cannot be 0, and I solve that, I have x cannot be -1. And that's the domain of this rational function. You can either leave it like that, and it's okay, it's sufficient to say what it cannot be, or you can change it to say what x can be. So if it can be everything else, we'll write that in interval notation as follows. So it can be -infinity all the way up to -1, and then we exclude -1 by using the open parentheses there, and then jump over it and pick it up again at -1 to infinity. So let's practice this concept with another problem. The next problem we're going to do is f of x is equal to x squared over x squared minus 16. Don't be tempted to try to do something funny with those x squareds. You can't cancel those. But what you can do is factor the bottom. So, So we'll factor the denominator. And what we get is f of x is equal to x squared over x minus 4, x plus 4. That's because the difference of squares factors. So following the last example, we know that this whole value right here cannot be 0. So when I rewrite it here, this is the not equal to that I'm solving. X plus 4, x minus 4 cannot be 0. Zero product property tells us if one factor or the other is 0, then the product will be 0. So if this factor is 0, the whole thing would be 0. So we're not allowed to have x minus 4 as 0. That means x cannot be 4. Or if this factor is 0, then the whole product would be 0. So the two values I'm not allowed to have in this domain are -4 and +4. And here's how you write that in interval notation. You come up from -infinity and you're going to jump over this -4, and then you're going to jump over the 4. So it is sufficient to say either what x can be or what x can't be. Both are okay for stating the domain. So this one right here, this is stating what x can't be, and this way is stating what x can be. So it's everything except -4 and 4. But this sort of can be confusing because that looks like, oh, that's the values that it is. Well, no, that's what it isn't. In this problem, we're going to practice composition. So we have two functions, f of x equals x squared plus 2x plus 1, and g of x equals x minus 3. And we're going to do composition on these functions. So f composed with g of x, and that means the function g is going to be plugged into the function f. So we can write that as g of x being plugged into f. So we're going to take this function right here and we're going to plug it in to f right here and here. So we'll circle that in pink. That function gets put in right there, and then it's going to get squared. It gets put in right there, and then it gets multiplied by 2. So what we have is f composed with g. By the way, that should be a small circle. It doesn't really look right. Let me see if I can get that smaller. There. And it looks like this. So just to be clear, here's the pink parentheses, and I'm going to put in x minus 3 and then square it. I'll do that on the next step. And then I'm going to plug in x minus 3, multiply that by 2 on the next step. So now I just need to simplify the problem and make it look a little bit more attractive. So now what we have is f composed with g of x is equal to x minus 3 times x minus 3 plus, now on this one I'm going to go ahead and do the distribution of 2 right here. So 2 gets multiplied by the x and by the -3. On the left hand side I still have f composed with g of x. On the right hand side I'm going to multiply these out. X squared, outer and inner together would make -6 plus 9 plus 2x, and then we'll go ahead and add the -6 and the 1. Now we'll combine like terms. There's not another x squared, so that's done. Then I'm going to combine the -6x and the +2, giving me a -4x. And I'm going to combine the 9 and -5, giving me a +4. So the answer requires function notation on the left hand side because we're building a new function. And then we see that's the composition of f composed with g of x. Now that is usually not the same thing you'll get if you compose g with f. So let's do the composition going the other way and see that we'll actually build a different function. So here I've rewritten the functions, and we're going to do the composition g composed with f. And just to remind you what that means that we'll first do the function f, and it gets plugged into the function g. So this time we're going to take this function and plug it in to g. And there's only x in one spot in the g function, so this way is actually easier than the last one. I'm going to have, to be clear, I'll put it in pink, the function f, which is x squared plus 2x plus 1, and that got put in right here. I still need to subtract 3 and then simplify that. So in this case I can just drop the parentheses and add like terms. So x squared plus 2x minus 2, and there's function notation on the left because we were building a new function. So the answer then is in the box. G composed with f of x is equal to x squared plus 2x minus 2.